did some detective work, and based on what I could figure out, I think that Group B is at 2 o'clock today and Group A is at 3 o'clock. So that's based on the fact that our last lab, everyone came at the same time because we were doing it during class, right? And the week before that, it was Group A at 2 o'clock. So if you go back through your notes, I think you'll come to the same conclusion. Anyways, that's what we're doing. And lab report 6 is due in lab today. And let me go over a clarification. I asked you to scratch out something in the formulas that wasn't correct previously. And I also updated the handout to be a little bit more descriptive. And so W, that pontoon mass, that includes not only just the weight of the plastic, but that also includes the traversing weight. And so for the other formula, you have to know the traversing mass separately, P, for this formula, but W includes everything. It's all in. And so if you were getting some large errors, it could be in part due to that mass measurement. I think when it came to Andrew, your calculations, the difference between the theoretical and the experimental was on the order of 5% difference, right? Maybe even less. Michelle?
So the experimental with W is the whole, like the pontoon and the transverse weight?
Right. That's right. Whereas P is just that transverse mass.
So what about the little rod that was holding the mass that had?
That rod goes along, well, that's in the everything, but the P is just the weight that moves.
Is that caused, I mean, I don't think it couldn't weigh that much, but it caused.
What, the rod?
Yeah.
You can go weigh it right now and see what it is.
Yeah. I don't think it would be enough to make too much of a difference.
I'm not sure. It could, but yeah, I apologize for any confusion that goes along with that. The company that produces the equipment, their name is, oh boy, who is that made that bench? Armfield. It's a British company, and they provide the handouts, and this is one that's had a few revisions based on errors that were in previous handouts, and they just call it pontoon mass, and so for future classes, will provide a little bit more instruction to make sure that you know it's the pontoon including all the weights. Okay. Another thing is that on this lab, you're going to be providing a printout of your Excel spreadsheet. And what I asked you to do is explain to me how you calculated each column. And just to give you an idea of what that looks like, this is a spreadsheet that I handed out to my hydrology class today. And so in each, I have various columns here. Here's a table, and I'm using Excel to calculate stuff. But below the table, I have a bunch of rows, and I explain how I got, or what is in, each one of these columns. And so here I say, T in hours is the time of interest specified by the problem statement. And so that, you couldn't put all of that in the column, because then the column would be too wide. You don't want to have a table that's a mile wide. And so the solution to that is that you can put in the formula or a description below the table. And so in your lab, what I'd like you to do is for each one of the columns that you calculate, have a row beneath the table that explains what's inside of each of those columns, or the formula that you used. All right?
Can we handwrite that? It's already been printed out.
Yeah. Yeah, the lab's not due until 2 or 3, as the case may be, so. Well, now see, the thing is when I'm looking at the spreadsheet, I don't want to flip back through the report and find the explanation of what's in each column. I want, as I look at the spreadsheet, to be able to just look beneath the table and immediately understand how you calculated different things. So I do prefer for it to be immediately under the table. Well, let me not grade it right now entirely. No, that's not. Because, well, let me modify that. You've got the column, so normally students don't go so far as to put the row and columns. Like this is showing the equation in terms of A, B, C, D, but since you've got the A, B, C, and D, that's okay. I'd rather have the actual formula. But that's passable because you do have the rows and the columns notated, and most of the time when people do that, they don't bother to provide those. Yeah. All right. All right. So the effect of this is twofold. Not only does it help me to understand your spreadsheet a little bit better, but more importantly, it helps you to understand your spreadsheet better. And this is something that will come up again and again in your career. Is you're going to be working on a project and it'll make perfect sense to you in the moment, and you can just speed through calculations, and it would be really easy not to write notes and explanations on how you got certain things. The documentation just seems like it's slowing you down or it's a waste of time. But then give yourself 2 years down the road, 3 years down the road, when whatever you designed is actually being built, someone inevitably is going to come back to you as a designer and say, hey, why was that pipe 18 inches? And you're going to be thinking, oh, I've done like 7 other projects since then. I don't know. You've got to go back through your calculations from start to finish, and you can either have these explanations and it's really easy to pick it up again, or you can start from scratch and just have a bunch of spreadsheets that are impossible to interpret. And so the take-home message I'm trying to communicate to you right now is that when you do good documentation, it's for your own benefit as much as for the client or for maybe the professor who's grading it. You'll come upon a case where you're going to want to repeat the calculations again or understand what you did, and taking just a moment to explain to yourself how it all worked is really great. I mean, I'll just a year, 1 year to the next, I'll forget how to do calculations that I've done, a dozen times before. And so I've started doing this for my own benefit because I do illustrations in class and I'd kind of forget how I was doing a certain method, maybe water surface profiles, and so that's something I'd like you to get in the habit of doing now.
How are you entering those formulas like that into Excel?
Okay. If you want to type in a formula in Excel, then you can do insert, object, let's see, they've changed everything around so much. Well, really, what I did was I started off, these are equations that I wrote in PowerPoint, and so I did insert, they've hidden object, insert. Yeah, I'll have to get back to you because it's not this equation thing. It's essentially inserting an object. In the old version here, it's like insert object, and then you choose the Microsoft Equation Writer, Microsoft Equation 3.0, and then you just start typing it in using these controls. It's a lot easier than some other approaches.
Those controls are the same as equation.
No, they're not. They're a little bit different. And it's just recently I'm writing up a journal paper, and the journal paper specifically says not to use this equation thing. Oh, I just saw object. It flashed for a second there. Insert. Where was it? Well, I'll try and find where it is in the new version of
This is not to do insert.
yeah, they say not to use the equation writer. Yeah, it's not that. It's different. The controls when you get into an object equation are a lot more robust and easier to use. So let me get back to you on that. Are you using the new version of Office 2013? Yeah. All right. I'll do some investigation work and I'll get back to you.
The worst thing about it is I started on the new version, tried to take it home and finish on the old version.
Yeah.
Can't even enter a formula on it.
Yeah.
It's got all kinds of errors.
Yeah. I feel your pain. Okay, the homework assignment that's due on Thursday, here's the set. You've seen that before. Just a little bit of guidance on problem number 5. It gives you some options, and it can be more than one of the options that apply on that particular problem. So it's not just one of the 4 options. It might be 2 of the 4 options, just as a hint. All right. So that assignment will be due on Thursday. All right. So any questions on the announcements before we get into the content? So these are the people who are submitting the labs and don't want them back for now, right? Okay. What's that? You're going to get it? Okay, that's fine. We'll do that. Let's do a flow visualization example. I've got a handout for you here. This is just to drive home how to draw streamlines, streak lines, and path lines. On the homework problem you've got, it says, you know, the flow is moving a certain u and v direction. And what you can just interpret that to mean is it's a coordinate system. And so you could say that u, what they are calling the u velocity, is a velocity in the x direction, for example. And the v you can take to mean is a velocity in the y direction. And I think that'll make it a little bit simpler to move forward. But just to eliminate any doubt, let's work through this example here where what I've shown you with the windows is the direction the flow is going. On the first part, we're going to draw the path line, which is easy. And then on the second part, we're going to draw the streak line, which is also easy, but a little bit harder. And remember, the key with the streak line is that you hold your pencil steady and you move your paper according to the direction indicated by the flow arrows. And so read through that, give it your best shot. It's okay to collaborate with people sitting next to you. Then I'll show you what the solution is. Just one other thing that I'll note is that when it's going sideways from time 5 till 9, it's going at a velocity of 1.41 times the velocity that it was going otherwise. And the reason why I said that is just so that it would still be a single block. So assume that it's going a little bit faster when it's going at the angle. So I'll give you a minute to read through this, try and figure out what I'm saying, and we'll go over the solution. Okay, so the water was flowing to the right for 3 seconds, so it pushed the particle to the right for 3 seconds. And then it was going 2 seconds down, so it pushed the particle down for 2 seconds. Then from seconds 5 to 9, it's going sideways, so 5, 6, 7, 8, 9, and then 2 seconds to the side, 1, 2. So this is the path that would be traced by a particle that is getting pushed around in the flow field. And that's just at one instant in time, a particle is released at A. Now, any questions about that? That one's the easy one. The streak line is a little bit more complex, and what I did on the streak line was I provided a scratch paper. It says here the grid on the right is scratch paper. So I used the scratch paper to get the shape of the streak line, and I don't know exactly where it's going to be until I'm done drawing it. And once I've drawn the shape of the streak line, then I transpose it onto the correct location. So I held my pen here at the origin, and then I started pushing the paper in the direction indicated by the arrows. Let's wait for it to focus. And okay, good enough. The paper needs to move to the right for 3 seconds, and so you can actually move the paper or just concede that if the paper is moving to the right, the pen's moving to the left for 3 seconds. Then the paper's moving down, meaning that the pen goes up for 2 seconds. The paper's going sideways from seconds 5 to 9, so that means I'm going to go the opposite direction in drawing my pen. And then the paper's going to the right, so that means my pen's going to the left, really. So this is the shape of the streak line, but it needs to be transposed because in the problem statement here it says that the tracer is added at B. And so that means at the end of the 11-second time period, this is where the tracer has been injected the entire time. And what's moved around is just the location of the previously injected tracer. And so I take this shape, and I know that this is the end of the line, and so I just draw it again where the end of the line will be at the location that the tracer has been injected all along. So I'll give you a moment to copy that down. If it didn't come naturally to you the first time, hopefully you can work through it again and get an idea of how this flow visualization works. Flow visualization is used a lot in mechanical engineering when it comes to cooling. What they'll do is, if they want to know how well a fan is working, for example, they can put smoke into a room, and they'll have special cameras, and they'll they'll light the room with maybe a strobe light or with different configurations of lighting that allows you to see the movement of particles, and so you can characterize the velocity of wind coming off of a fan, like if it's a cooling fan for a CPU in a phone or something like that. Yeah. Well, because it was always injected at B the whole time. This is the location. Like, think about if it's a river that's moving around, and we're in a helicopter above the river, and we're just pouring in paint. And so what's moving is the water itself is moving, but we're still hovering over the same physical location, pouring in paint. This is what it would, this is the, from above, what the streak would look like if we'd been pouring in paint that same time. And so this is where it was all injected, and then this is the evidence of where the flow had been in the past. So what you're saying is, well, it's going to be spreading out. Yeah, yeah. So it would be more diffuse, and then it would be tapering down, and it would be more, if you're considering the effects of diffusion, then yeah, it would be lighter here, because it would be diluting itself. Yeah.
It was starting at B, why wasn't that T0? I understand the directions wouldn't matter.
Yeah.
But
Well, the first particle of paint that we poured in was the particle of paint that now is right here. T = 0 means this is the original paint that got poured in, and it's just been moved around, and now it's there.
so where's the, like you said, like the light is like spreading
Yep.
out, that's gonna be the
Mhm.
T0.
Yeah.
What about the path line on top? Now, what is it? I mean, I get the bird's eye view. That makes a lot more sense to me. But as far as the path line.
The one on top means it was just, think about, instead of pouring in paint continually from the helicopter, we just dropped a single can.
And then that's the way it would flow.
That's the path that got traced, yeah.
But that's still from a bird's eye view on top.
Yeah, it's looking from above. So, there's a similarity in the shape, but it's not just a simple reflection of it. All right. So I hope that illustration will help you on the homework problem you've got where you need to draw and interpret the streamline, streak line, and path lines. Last time when we finished up, we were doing an example that had to do with convective acceleration. And in that example, it's easy to get lost in the chain rule and sort of miss the greater point. And the greater point was that what we're calculating is the acceleration at a point, meaning that the shape of this nozzle is accelerating the fluid. And so there, you just take it as a given. There's some piece of metal, and that metal forces the water into a smaller cross-sectional area, and so it comes out with a big velocity compared to the small velocity that came in. Think of your thumb over the hose. When you put your thumb over the hose, you're giving the water a smaller diameter to flow through. Originally, here's the hose diameter, and when you put your thumb over part of it, you cover it with your thumb, now the water can't flow through that part of it. And so it has to have a higher velocity to get through the smaller cross-sectional area. So this nozzle is accelerating the fluid, acceleration being that the velocity out is greater than the velocity in was. Just to summarize what we did in that example, we had some equation that told us what the velocity was as a function of position. We were measuring our distance from the entrance. From here, that way, we were measuring our position, and that's x. When we were half of the way from the entrance to the exit, when we were at this midpoint location, we wanted to know what was the acceleration at that point. And so convective acceleration is the velocity at a certain point multiplied by du dx. And so that's the definition of a sub x. And remember, in our discussion of acceleration last time, we differentiated between a sub L, which is local acceleration, and a sub x, which is convective acceleration. Uh-huh.
coming up with that formula.
Well, this formula isn't what came out of the chain rule. That formula is what we put into the chain rule. We put this formula in here when we were doing du dx. And so we use the chain rule to find what is du dx of this equation. Yeah. And if it would be helpful, I could scan and email a PDF of that example if you'd like to have that. So I'll send that to you after class. All right, so let's just take a step back and talk about the types of flow that we've discussed so far. We've talked about steady flow, which is when the velocity is constant with respect to time. We talked about uniform flow when velocity is constant with respect to position. And that gave rise to local acceleration, which is dv dt, and convective acceleration, which is defined at a certain point in the flow field. And so it's specific to a position, and it's v dv ds, where s is a change in location. So how is the velocity changing as a function of some distance away from another point? And so s in this previous example was just the direction, the x direction was what we used as our measurement of position. So here in this, the s means position. Yeah. So local acceleration is associated with unsteady flow. You have unsteady flow when there is a local acceleration. And you have non-uniform flow when there's convective acceleration. Let's go back to those pictures I showed you a few lectures ago of steady versus unsteady. Okay, so let's look at these flow patterns. We talked about how this is uniform flow, this is uniform, and the way that we know it's uniform is that the streamlines are parallel. So uniform flow means that the position, that the velocity is not changing with respect to position.
In this upper one, above that, that kind of to the right, yeah, that.
Mhm.
Would those not be considered parallel? Or just
No, they're not parallel. The way to, you can tell that this one is sloping downward and that one's sloping upward, and so this line and this line it's getting closer together. If you measure the distance, how far away is this line from that line on the left-hand side, it's further away than on the right-hand side, which is proof that they're not parallel. It doesn't look very different, I agree with you. So uniform flow, the bottom ones. The ones on top are non-uniform because we know that the velocity is changing with respect to position. Now remember, velocity is a vector for this rotational flow. Even though the magnitude of the velocity may be constant, the position component of the velocity is changing, like its direction. All right. So local acceleration and convective acceleration. What we're going to be moving on from here is, in today's lecture, talking about something known as Euler's equation, which is the application of local acceleration to the question of what is the pressure. Here's the main question. What is the pressure? Yeah, it is. What equation have you used to answer this question so far? Right. Delta P is delta H times gamma. Hydrostatic equation. Euler's equation is going to allow you to answer the question, what is the pressure in a different situation? Hydrostatic equation, when could you apply that? You could apply that when you had static conditions, when the water wasn't moving. Euler's equation allows you to answer the question, what is the pressure when local acceleration is happening? So when there is unsteady flow, Euler's equation will allow you to determine how the pressure changes in the flow field. Likewise, Bernoulli's equation, which we'll get to in 2 lectures, answers the question, what is the pressure when there's convective acceleration? And so remember, local acceleration is when over time the velocity is changing. And Euler's equation is going to let us answer the question, what's the pressure? Okay, so Euler's equation models the change in pressure due to a fluid acceleration. And specifically what we're talking about is local acceleration. We've already been through the hydrostatic equation for static fluid, where we've got some tank of water and a delta H, and we want to know the pressure at a certain depth. Euler's equation goes a step further. It's an extension of the hydrostatic, because what the hydrostatic equation was is, where is the acceleration in here? The hydrostatic equation has acceleration built into it. So where is it? In the unit weight, right. So we could rewrite that as delta P is delta H, density, and G. So the acceleration was always there. It was in the definition of the unit weight, since unit weight is density of the fluid times G. So hydrostatic equation talks about fluid that is being accelerated, but it's being accelerated only at G. So what if the fluid is being accelerated at some different acceleration besides gravitational? That's what Euler's equation will allow us to do. And just to give an illustration of that, okay, instead of being a stationary tank, what if it was being accelerated upward and delta H was 1 meter? So how would that affect the 1 meter? What we could do is we can try saying, let's just, instead of having this G be 9.81, let's have it be twice 9.81. Okay, in that case, this is just to give you an idea of where Euler's equation is heading. This isn't Euler's equation itself, but it's just sort of the essence or a preview of Euler's equation. We could say delta P in this case is going to be delta H times the density of the fluid, and then there's going to be G plus some other acceleration plus another G. And the other G we're saying is the original gravitational acceleration, and now since it's going up at 9.81. So plus another G, because it's accelerating upward at 9.81 meters per second squared. So the delta P would be delta H, so it's 1 meter, we've said is the delta H in this problem. And it's water in this tank, we'll assume, has a density of 1,000 kilograms per cubic meter. And then we have 9.81 meters per second squared plus 9.81 meters per second squared. That means that the change in pressure would be equal to 19,620 newtons per meter squared. So the pressure increase would be double because the acceleration is double what it's normally experiencing. Absolutely. So what if it was accelerating downward at 9.81 meters per second squared? Then you could go up and down through the fluid and there would be no pressure change. So if you have a tank of water, well, you're scuba diving in a tank of water, that all of a sudden starts accelerating downward at 9.81 meters per second squared, then there is no delta P if it's accelerating down at 9.8 meters per second squared. Or what if the acceleration was sideways at 9.81 meters per second squared? Then if it was accelerating sideways, then the change in pressure due to vertical change would be the same as if there was no acceleration. So that's where we're headed in. And we'll get more specific about this sideways thing. If that should take your mind a little bit to wrap around the idea of the sideways acceleration. So we'll go into more depth with that. That's a good question, though, because yes, the direction of the acceleration has a huge impact. So let's say we've got some element of fluid. We've just got an amount of fluid, a certain amount. And that certain amount has a cross-sectional area. It's a cylinder in shape for some reason. The cylinder has a length of delta L, and it's being accelerated in the L direction, and also gravity is acting on it. Okay? So let's consider all of the forces that are coming into play here. So this is an element of fluid that has pressure acting on it from beneath. So you can see delta P times A, where delta P is having to do with how deeply submerged it is. And then there's P plus delta P times delta A. So it may be that the cross-sectional area of this element is changing, and also it's being accelerated in a certain direction. That means that the pressure isn't going to behave just accordingly only to the hydrostatic equation. Some of the questions we need to ask when we start applying Euler's equation is, what's the mass of the element in question? What are the differences in forces relative to cross-sectional area? What are the factors causing change in pressure between the two faces? And so the reason is, why is there a change in pressure from this side of the element to that side of the element? Part of the change in pressure is due to the static effect, or the effect of ordinary gravity, but then part of the pressure change is also going to be due to the acceleration that's beyond the gravitational acceleration. The directionality and the change of pressure, let me write down a phrase that you should copy in the margin next to this slide, and that is, the pressure decreases in the direction of acceleration. So what that means is that if you have an element of water and it's being accelerated this way, then the pressure is going to be greater. The pressure in the fluid will be greater over here than there. So this would be high pressure on the left side and low pressure on the right side. And so the acceleration was to the right, but the increase in pressure was to the left. And so here in the statement, what I've said is the pressure decreases in the direction of acceleration. If you've got a space capsule that's being accelerated upwards through space, then the astronauts are pushed against the seat. And so here, if we were accelerating it to the right, the increase in pressure is to the left. And so there's a decrease in pressure in the direction of acceleration. So the main thing, the directionality and the change of pressure, Euler's equation tells us that it decreases in the direction of acceleration. Now, I don't think that Euler's equation is in that fluid mechanics packet that I gave you from the FE manual. And so that means I'm going to provide you with Euler's equation in a quiz or an exam. And this is the version of it that I'm going to provide. What you'll need to know how to do is how to apply this equation. And it's not a derivation so much as just applying it to the coordinate system from the problem itself. And so here is the development of what you need to do in order to be able to apply Euler's equation in a homework problem or in a quiz or an exam. What Euler's equation says is that you've got piezometric pressure, P plus gamma z, that's piezometric pressure. The change in piezometric pressure in the L direction is opposite of the acceleration times the density of the fluid. And so the opposite sign here, the negative, is because of what I've just described, that the pressure decreases in the direction of acceleration. So that's why there's a negative sign here. And the L direction could be x or it could be y. It's whatever direction the acceleration is occurring in. You have to read the problem statement to see if water's being accelerated upwards or to the side or whatever the case may be. So if you assume that there's linear variation in pressure and that the x direction is what we're going to be using for L, then you substitute this partial differentiation for just in linear variation. You assume there's a change in the pressure, the piezometric pressure, with respect to some incremental distance x. So delta x is a distance. And the delta here is talking about the change in piezometric pressure between 2 points over some distance, delta x. Density of the fluid between the 2 points and the acceleration that this is being moved in. And now, this is finally how you could actually start substituting things into Euler's equation, is when you say that the change in piezometric pressure, so delta piezometric pressure, the way that you expand that out is it's at location number 2, the pressure plus gamma times z, where z is some elevation above the datum, minus the pressure plus gamma z at location 1. And then you move the delta x and the negative sign over here to the right-hand side of the equation. So now we've got the negative sign, delta x is some distance, the density of the fluid, and the acceleration in x. I realize this probably feels really abstract so far, but we're going to apply it to an example problem here in a minute, and you'll see exactly what I mean by, p plus gamma z2, p plus gamma z1, and so on. Any questions so far?
So far, maybe it's the y direction.
All right, yeah, so what if it was in the y direction instead of the x direction? How would we apply Euler's equation in y? So if it was in the y equation, then we'd say for the y direction, then it would be delta y p plus gamma z equals the density and acceleration in y. And so then it would be p plus gamma z2 minus p plus gamma z1 is equal to delta y, negative delta y, density, acceleration in y. Now, the coordinate system is easy to get confused on when we apply Euler's equation. We're going to assume that when we say y, that usually means up, right? Well, z also means up. So don't let that confuse you. You can use y and z to mean the same thing, up, in this equation. We'll be working in 2 dimensions. We'll be working in 2 dimensions. Now, what we mean by 2 and 1 is if we're working in the x direction, then location 2 is the location that has the most x direction. So, for example, let's say here is x and here is the z direction. If it's being accelerated to the right, then we want to know the pressure difference between 2 points. Then the point that has the most x is location 2. And this is the number 1 problem that students face when they're applying Euler's equation, is they switch location 1 and location 2. And that's not a minor error. Like on the exam I handed back, I'd take off maybe 1 point or 2 points for a minor error. But if you mistake location 1 and location 2 on problems like this, it's a major error. And so that would be like minus 6 points or something. It's a huge thing to get location 2 and location 1 right. So through the example we're going to work, I hope that you'll get a sense for how to pick which is which. So let's say we've got a tanker that's carrying gasoline. It's driving down the road, and it's got gasoline in the back of a box truck for some reason. Let's just assume that it's not leaking out, but it is open to the atmosphere here at the corner. You can see that it's saying the pressure at that corner is 0. And so it's gauge pressure is 0. It's open to the atmosphere. It's accelerating to the left at 3.05 meters per second squared. So since it's slowing down, that means that the acceleration we're going to use is negative. Its acceleration is opposite to its current direction, and its current direction is to the right. So in this example, we want to find out what's the pressure at A and where is the pressure the greatest. Okay, so first of all, the pressure at A. All right. We've got an instance where we are going to have Euler's equation that we're applying first in the x direction. P plus gamma z, density, acceleration in L. Okay, so we're going to say for L is equal to x, then this turns into delta x P plus gamma z is equal to density A in the x direction. And the way that we're going to use that is P plus gamma z at 2 minus P plus gamma z at 1 is equal to the negative delta x, density, and acceleration in x. Now the acceleration in x is negative 3.05 meters per second squared. The negative sign because it's slowing down. It's moving to the right, but its acceleration is to the left. And I've defined this to be the positive x direction, and this is the positive z direction. I'll use z to describe vertical. In the problem, we know that because it's gasoline, its density of the fluid is a little bit lower. We've got 6,600 newtons per cubic meter. And that makes the density of the fluid, if we have density is gamma divided by g, it's 672.8 kilograms per cubic meter. All right, so where is location 2 and location 1? Location 2 and location 1. Now on the previous slide, what it told us is you pick the, for the direction is x, and that's what we're working in. Location 2 is the one that's furthest to the right, and location 1 is the furthest to the left. And so in this example, we're going to work Euler's equation between this opening and over here to A. We're going to try and find what's the pressure difference from here, where it's 0, to over there, where it's A. And this is a case where, remember, in hydrostatic equation, the pressure difference when you've got two points that are only horizontal distance away from each other, there's no depth distance. In the hydrostatic equation, it would say that there's no pressure difference between the opening and location A. Because hydrostatic equation says that pressure only changes when you go up and down. But here, we're going sideways, and the pressure is going to be different because it's decelerating. Do you think that the pressure at A is going to be greater than the pressure at the opening or less than the pressure at the opening? It's going to be greater than. You just think about, all of that water is pressing up against this side of the truck because it's slowing down. So where does the water want to go? The water is sort of sloshing up against the right side. Now it's not actually able to move because it's full to the top, and so it's not like it's moving around in there. The physical location of the water, of the gasoline isn't changing, but the pressure is reacting to the acceleration. Now the whole point of Euler's equation is to predict what is the pressure change due to this local acceleration. And so what we know is location 2 is going to be what we call A, and location 1 is the opening. So we're going to, first of all, find out, we're going to have the pressure at A plus gamma Z at A minus the pressure at the opening minus gamma Z at the opening. And you'll notice here I've distributed the minus sign through this expression here. So we've got minus P minus gamma Z, all right, is equal to negative delta X, the density of the fluid, and the acceleration in X. So is everybody with me so far? Any questions? I encourage questions in class. I want you to ask questions if you've got them. All right. All right, so now, how does the elevation of A compare to the elevation of the origin? If we're measuring elevation from the bottom of the truck, for example, they're both 1.83 meters above the bottom of the truck. And so we can cancel out this whole term because ZA and Z naught are the same, because vertically wise, they're not any different. So that leaves us with
Why does the elevation even matter? I thought you said if it's sideways, that like should A and B's pressure be the same?
No, A and B's pressure in this case won't be the same, because not only is it accelerating to the left, but also there's still gravity. So gravity is still going to make the pressure at B greater than the pressure at A. Yeah. And so we don't always cancel out this term that I've canceled out here. We could go directly from the origin to B, and then it would matter. I'll illustrate that. All right, the pressure here at the opening is 0. And so we're going to calculate the pressure at A is just going to be negative delta X, the density, and the acceleration in X. Okay, so that is negative 6.1 meters, the density 672.8 kilograms per cubic meter, and then negative 3.05 meters per second squared. So that gives us a pressure at A is 12,517 newtons per meter squared. Really what we've done is that's sort of like the hydrostatic equation. If you think about it, we had some delta X is the distance part of the equation, and then the density times the acceleration, that's kind of like the gamma that we were doing in the hydrostatic equation. So it's sort of like a sideways hydrostatic equation, except for it's not static, because the acceleration here isn't just talking about gravitational, it's some other local acceleration that's being experienced. In this case, the way that gravity didn't matter is because they're at the same elevation. Yeah. Now,
But if they're going down, if the truck is going downhill.
well, no, if we pick different points, gravity would matter. So when it comes to where is the pressure greatest, part 2 of this question, all of a sudden gravity is going to matter again. Gravity is going to matter if we find the pressure difference between the opening and location B. I think we can all agree that the pressure at B will be greater than the pressure at A because, you know, this truck is driving down the road. It's not floating in outer space. And since it's driving down the road, we know that gravity applies. And so since gravity applies, the effect of the hydrostatic principle will be felt at B. So now in the second part of this example, let's just find out what is the pressure at location B. Pressure at B. Okay, it's still that we're applying Euler's equation between 2 points, so it'll be the pressure plus gamma Z2 minus pressure plus gamma Z1 is equal to negative delta X density acceleration in X. All right, so when we're considering the origin versus B, which one should I say is location 1, and which of them should I say is location 2? The origin is it is higher, more to the left. B is lower, more to the right. Okay, so which of them is location 1 and which of them is location 2? Kia, do you have an idea? No? That's okay. Marcus? It would. And why did you come to that conclusion? Oh, nope. That's not why. You got to the right answer the wrong way. Sometimes that doesn't matter. This time it does. The one that's furthest to the right. So one of them is higher than the other, but we don't care which one is higher because the acceleration is in the x direction. So since the acceleration is in the x direction, really what we're asking is which of these 2 points is further to the right? And location B is the one that's further to the right. So that's why we're going to call it 2. Now if it was a vertical acceleration, then all of a sudden we'd have to worry about which one has more z. And the origin would have more z. So if we were working this problem about a vertical acceleration, then 1 and 2 would be switched. But here, what's that?
Does it matter? When you do the calculation, do the mathematical.
Yep. Yeah, if you picked 1 and 2 wrong, then you'd get different numbers. Yeah. No, we'll see how it would foul things up. When we start substituting in the numbers, you'll see here. Okay, so what that means is we've got the pressure at B plus gamma ZB minus the pressure at the origin minus gamma Z at the origin. Again, that negative sign goes through to there. Okay, is equal to negative delta X density acceleration in X. All right, so the pressure at B is the unknown. We want to know what is the pressure down there at B. And we're going to be using the bottom of the truck as our elevation datum. And so let Z equals 0 at the bottom of the truck, and that means that up at this point, Z equals 1.83 meters. Okay, so the pressure at B is unknown, plus the gamma, which is 6,600 newtons per cubic meter, times 0 meters, because Z of B is down at the origin of the datum, minus the pressure at the origin, which is 0, minus gamma times Z naught, and the Z naught there is the Z at the origin is 1.83 meters, is equal to negative delta X. Now how far apart? What is the delta X between the origin and B? That's just, well, no, it's just only in the direction of X. It's not the total distance between them, it's only the X component of the direction. Yeah, so it's going to be the 6.1 meters, and then the density, 672.8 kilograms per cubic meter, and then the acceleration, negative 3.05 meters per second squared. Does anybody have any questions about why I've picked a certain value so far in substituting to the equation?
The method that we used here to find the location of the exact that's case specific.
It depends on the acceleration direction. We can use the same method always, but it depends on if it's being accelerated up or sideways, or sometimes it's being accelerated up and sideways at the same time. And in that case, you have to apply Euler's equation twice. All right, but here we've only got acceleration in the x direction, and Euler's equation has built into it the hydrostatic equation. It's built in, so we don't have to separately account for the hydrostatic effect. That's built into Euler's equation right here. All right, so here if we continue with this, we've got the pressure at B is equal to 12,517 newtons per meter squared plus 12,078 newtons per meter squared. Those two different components, there's the component that is having to do with the change in elevation, and there's the component that's having to deal with the local acceleration. And when we combine them together, it's 24,595 pascals. So that is the pressure at B. All right, if water is accelerating through a pipe, then you can find the pressure difference due to that. Let's say that we've got some horizontal pipe, and the water, we want to find out what pressure is required to cause a local acceleration of 6 meters per second squared. So if the speed of the water was increasing through the pipe, what pressure difference would be causing a certain acceleration? Okay, so in this case, rather than finding the pressure when it is like a single element of water that's being accelerated, or a single element of fluid, like the gasoline was in a truck, here it is a fluid inside of a pipe that's accelerating. So it's a pressure gradient, really. For the pressure gradient, we've got a horizontal pipe, and so the elevation differences are going to be negligible. We're going to have the Z2 is going to be equal to Z1 when we start substituting in Euler's equation. So the expanded version of Euler's equation for an acceleration in the x direction is going to be the pressure at pressure plus gamma z at 2 minus the pressure plus gamma z at 1 is equal to the negative delta x density and the acceleration in x. Okay, so here we want to know what's the pressure gradient. And what that means is how much is the pressure changing for every meter of distance through there. And so we can select a 1 meter, if A and B are 1 meter apart. And we can find the pressure at B minus the pressure at A, where the elevation term cancels out because it's a horizontally inclined pipe, is going to be negative. They're 1 meter apart. The density of water is 1,000 kilograms per cubic meter. And then the acceleration here is 6 meters per second squared. And should we do a negative sign or not? Positive, because the water's flowing to the right. The acceleration says it's 6 meters per second squared to the right in the x direction that we've defined. And so the change in pressure would need to be 6,000 newtons per meter squared in order to cause the acceleration of 6 meters per second squared. So 6,000 newtons per meter squared per meter. So a pretty big pressure differential to get it to accelerate at that rate.
We're assuming the 1 meter?
Yeah, because it's when it's talking about a gradient, that means how much pressure per unit of length. So you're assuming that A and B are a meter apart because it said gradient. Okay, one last thing. I want to give you a little bit of assistance on problem 437. The way that problem 437 is written, they do you a real disservice because they suggest that what you ought to do is first find the pressure between A and C, and then find the pressure difference between B and A. Actually, it's easier if you flip that, and you start by finding the pressure difference between A and B, and then you find the pressure difference between A and C. So that's the first hint I'm giving you is flip the direction that it says to solve it in. It says to solve one thing and then solve the other thing. Do it in the opposite order. But really, let's talk about Euler's equation. What they're saying in this problem is you've got some tank of a liquid. It's not water. It's a tank of a liquid that has a specific gravity of 1.2. So that means the density is going to be 1,200 kilograms per cubic meter. We can get the density very directly from that specific gravity. And it's accelerating in two directions. Accelerating at 0.9 g to the right, and it's accelerating down at 1.5 g. So the suggestion I've just given you is start off by finding the pressure difference between A and B. If it's accelerating down at 1.5 g, let's just talk about this in conceptual terms before you even need to plug anything in. Where's the pressure going to be higher? Will the pressure be higher at A or at B? Ordinarily, the pressure would be higher at B, but in this case, the pressure is higher at A. Why is that, Zachary?
We're going pressure lowest where the acceleration is acting on.
Right. Since you're accelerating down at 1.5 g, that's overcoming normal, ordinary gravitational acceleration. You know, g would be, if it was accelerating down at g, then the two pressures would be equal. But here, it's accelerating down at more than g. And so the pressure at A will be greater than the pressure at B. And so in the first part of the problem, what you're doing is you're applying Euler's equation in the z direction. And so how does Euler's equation look when it's in the z direction? It looks like, what will be 1 and what will be 2? In z, okay, for the z direction, and we want to find the delta p for, not for, I'll say between A and B. So 1 and something's going to be called 2. Why will A be 2? It is.
Because it's, well, I just kind of flipped it over on the side because the way you're talking in the x direction is furthest to the right, so it'd be the furthest from the board.
Yeah.
So I'm calling B the board.
All right. So location B has less z. It's further from the origin. A is further from the origin. It has more z. Our z direction is up, and so we're going to say that location 2 is A and location B is Location B is 1. And so then if we use Euler's equation, it's going to be the pressure at A plus gamma ZA minus the pressure at B minus gamma ZB is equal to the negative 4 feet, because that's the vertical distance between them, the density of it, and the acceleration in the z direction. That's the application of Euler's vertically.
And would you subtract this 1.5 feet and subtract it off of that?
No, it's built in. We don't have to manually overcome that. So for the acceleration, you do, the acceleration is down, so you're going to say negative 1.5 times 32.2 feet per second squared. So Andrew's question is, well, do we subtract, the g, and is it only just the leftover half a g? No, because remember that this part of Euler's equation handles the static side of things. So this is already taking into account what would happen if there wasn't any extra acceleration. So this part is why you don't have to, the left-hand side of the equation. Do you have a question, Levi? Okay.
Why we call it Z instead of Y?
Just because Euler's equation has z here, and it's the same thing really, it's elevation. We're saying that z is the vertical component that the static conditions are causing. Like in the hydrostatic equation, sometimes we called it z instead of h. Yeah, just to confuse you, really. Okay, so what about, so that part in the z direction will allow us to find the pressure difference between A and B. It'll be some pressure difference you can calculate. And then, so in the problem statement, they said find the pressure difference between C and A. So we know we can jump from here to here. The next thing is you need to jump between B and C. So if you find the pressure difference between B and C, then instead of working in the z direction, now we're working in the x direction, right? So here for x direction, okay, so which is going to be 1 and which is going to be 2? Okay, whatever has the most x will be 2. What has the least x will be, we're going to use 1 for C because it has the least x. And so to apply that to Euler's equation, it's going to be the pressure at B plus gamma ZB minus the pressure at C minus gamma ZC. And by the way, this is another place where I see a lot of errors. Everybody know why I'm putting a minus sign there? It's because of it's getting distributed. The one that here is here. If you multiply that -1 times that, it's going to be minus gamma z. So that's another common place that people get tripped up. Okay, so this, and so in the x direction, then it would be is equal to negative the acceleration in x. First of all, the delta x, so that distance is 3 feet. The density of the fluid, and then the acceleration in x. So 0.9 times 32.2 feet per second squared. And it is accelerating to the right, and so it's a positive there. We don't have to change the sign of the acceleration. That's right. They're at the same elevation. So ZB and ZC are going to be equal. So going through that step will tell you the change in pressure between B and C. And so, you did A to B, You did B to C, therefore you can find A to C. You have to combine the two together to answer the main overarching part of the question was, what's the pressure difference between C and A? You do it in 2 steps. You can't go directly from A to C, not when there's 2 accelerations. No, it's not that way. It's cumulative. All right, see you in lab today. Oh, by the way, here's how you type in the equation, real quick. Okay, Word, you go to Insert, and then there's this box right here, the unnamed box, Insert Object, and then Microsoft Equation 3.0. So that's how you get to it. Huh? They do. They hide the important things and they make the irrelevant things real easy to find.